Jai Hind everyone. In this lecture of the subject Energy Science and Engineering KOE 033 as per AKGEC syllabus, I am going to discuss various forms of energy, conversion of energy and the physics involved in power plants as far as the energy conversion is concerned. These are the contents of this PPT of this lecture. Energy, various forms of the energy and the physics of power plants. So, starting with the energy. Energy is the quantitative property that must be transferred to an object in order to perform work or to heat the object. Energy is a conserved quantity. The law of conservation of energy states that energy can be converted in any form but not created or destroyed. So, energy conversion can take place. We can convert any form of energy to any other form, but we cannot create or destroy the energy. The SI unit of energy is the joule, which is the energy transferred to an object in moving the object by a distance of 1 meter against a force of 1 Newton. There are some other units of energy as well, starting with joule itself. So, as I just mentioned, the joule is the unit of energy in international system of units, that is in SI units. It is equal to the amount of work done when a force of 1 Newton displaces a mass through a distance of 1 meter in the direction of the force applied. It is also the energy dissipated as heat when an electric current of 1 ampere passes through a resistance of 1 ohm for 1 second. Other units of energy are as follows. A calorie. A calorie is a unit of energy. In nutrition, calories refer to the energy people get from the food and the drink they consume and the energy they use in the physical activity. Calories are listed in the nutritional information on all food packaging. Two main definitions of calorie are in wide use: the large calorie or the food calorie, or the kilogram calorie or the kilocalorie. They were originally defined as the amount of heat needed to raise the temperature of 1 kilogram of water by 1 degree Celsius or by 1 Kelvin. The small calorie or gram calorie was defined as the amount of heat needed to cause the same increase in 1 gram of the water. 1 large calorie is equal to 1000 small calories. Various other units of energy are: the units can be preceded by various factors and there are usually different units for measuring energy. Some common units include the British Thermal Unit or BTU to measure heat content of fuels or the energy sources. BTU is the energy unit which is used to measure heat content of the fuels or the energy sources. kWh or kilowatt hour. A kilowatt hour, otherwise known as kWh, is a way to measure how much energy you are using, how much energy we are using. Calorie, we have already defined the calorie. Then electron volts. Electron volts is the unit of energy which is commonly used in atomic and the nuclear physics. It is equal to the energy gained by an electron when the electrical potential at the electron increases by 1 volt. Hartree. Hartree energy is a physical constant equal to twice the binding energy of the electron in the ground state. Ground state is the lowest energy state. This is defined for the hydrogen atom. When a hydrogen atom is in this state, an amount of energy equal to 0.5 Hartree is necessary to free the electron and thereby cause the atom to become an ion. Rydberg units. The Rydberg unit of energy is used to calculate the energy levels in hydrogen spectrum energy, which is absorbed or emitted in the form of photons as electrons move between shells in the hydrogen atom. Barrel of oil. The energy contained in a barrel, of oil, which is approximately 5.8 million British thermal units or 1700 kilowatt hours of energy. The energy contained in a barrel of oil is approximately 5.8 million BTU or 1700 kilowatt hours of the energy. So these were the basic units, some common units of the energy. Now let us talk about the forms of the energy, various forms of energy. Energy comes in a variety of forms, and these forms may be transferred into one another. Energy comes in 6 basic forms. These 6 basic forms are chemical energy, electrical energy, radiant energy, mechanical energy, thermal energy, and the nuclear energy, right? You may find additional forms mentioned such as electrochemical, sound, electromagnetic, and others. However, many additional forms are actually the combinations of these 6 basic categories, these 6 basic forms of the energy. Starting with the chemical energy. So, chemical energy is energy that is stored within the bonds between tiny parts of a substance molecules. Some common examples of chemical energy are energy contained in fuels such as coal, gasoline, natural gas, and even sugar. When our bodies burn sugar during exercise or workout, the sugar components are reorganized, and in this reorganization of the sugar components, some amount of energy is released. That is due to the change in chemical bonds of the original substance. Electrical energy. Electrical energy is energy from moving electrons. It is the type of energy which is obtained from movement of the electrons. Some materials, particularly metals, have electrons that are only loosely attached to their atoms. They can easily be made to move from one atom to another if an electric or magnetic field is applied to them. When those electrons move among the atoms of matter, an electrical current is actually created. Radiant energy. Radiant energy is the form of energy which is associated with the movement of light, electromagnetic waves, or the particles. So, energy associated with the movement of light, electromagnetic waves, or particles is said to be the radiant energy. The radiant energy includes visible light as well as other forms which are not visible to an unaided eye. For example, the X-rays, gamma rays, radio waves, etc. Light, like the light from the sun, is one type of radiant energy. In fact, this energy is what makes the life on earth possible. Mechanical energy. Mechanical energy is the energy possessed by an object due to its movement or due to its position. Accordingly, we may call these energies as either the kinetic energy or the potential energy. In other words, an object possesses mechanical energy when it has the ability to do work due to its position or due to its motion. The mechanical energy takes the form of either kinetic energy, which is the energy due to movement of the object, or due to object's motion, or the potential energy, which is the stored energy due to the object's position. Nuclear energy. Nuclear energy is the energy released when nuclei of atoms are split or they are fused. Fission, that is splitting of atoms, is used to produce usable nuclear energy. Fusion, the fusing or combining the atoms or the combination of atoms takes place in stars like our sun. Thermal energy. Thermal energy is heat energy or the energy of moving or the vibrating molecules. They are, that is, heat and thermal energy are actually directly related to the temperature. Adjacent objects that are at different temperature will spontaneously transfer their heat to try to come to the same temperature. For example, let us take a hot cup of coffee in a cool room. When this coffee loses some of its thermal energy as heat flows from the coffee to the room, the molecules in the coffee slows down. The vibration of these molecules reduces as the coffee loses heat, and over the time the coffee cools to the room temperature and there is no further movement of the heat from the coffee to the surrounding. Now let us see what are the various states of the energy. In fact, all the energies can either be in the state of having potential energy or having the kinetic energy. So there are only two possible states of the energy as far as our discussion is concerned. They are the potential energy and the kinetic energy. Potential energy is actually the stored energy. It is the energy that is ready to go. For example, a lawn mower which is filled with the gasoline is ready to move to cut the grass. A car on the top of the hill, it is ready to move downhill. A book on the edge of the table, they all are the examples of the potential energy. Potential energy can be used in combination with other forms like gravitational potential energy. Gravitational potential energy is the energy of an object that is possessed by the object due to its height in comparison with a lower elevation. The other form of the energy, the other state of the energy is the kinetic energy, and the kinetic energy is the energy that an object possesses or that something possesses due to its motion. Let us see what are the various examples of potential energy. Some of the examples of potential energy are shown over here just to give an insight of how many types, how many forms of potential energy are there. Potential energy is stored energy of an object. We know that instead of coming from motion, it actually comes from the position relative to the others. For example, an internal stress, an electric charge or its condition. They may be the reason of the presence of potential energy. The object has the capability of producing energy as the condition changes. Right? This energy could be mechanical energy, chemical energy, electric energy, nuclear energy or magnetic energy. So I would call them mechanical potential energy, chemical potential energy, electric potential energy, nuclear potential energy or magnetic potential energy. Starting with the mechanical potential energy. Mechanical energy otherwise is the energy of movement. In fact, all items have potential energy based on their position. Gravitational potential energy and the ability to bounce back, that is due to elastic due to possession of elastic potential energy. When the potential energy of an object is combined with its kinetic energy, it actually results in the mechanical energy. Let us see the examples of gravitational potential energy. So, when something has a high position, its gravitational potential energy is high. For example, a book on a high bookshelf has higher potential energy than a book on the bottom shelf because it has farther to fall. Other examples of items with gravitational potential energy include a raised weight. The example which I have quoted over here are the example of the raised weight. Water that is behind a dam is an example of potential energy, gravitational potential energy. A car that is parked at the top of the hill. It is also an example of gravitational potential energy. Once allowed, the car will start moving down the hills due to the effect of gravitational forces. A yo-yo before it is released. A yo-yo is ready. A yo-yo which is ready to get released is actually containing the potential energy. And once the yo-yo is released, the potential energy gets converted to the kinetic energy. River water at the top of a waterfall, a book on a table before it falls, a child at the top of a slide, a ripe fruit before it falls. They all are the example of gravitational potential energy. Let us see the examples of elastic potential energy as well. The material an item is made of can affect the material an item is made of can affect its potential energy as well. For example, an elastic ball has higher electricity, an elastic ball has higher elasticity than a bowling ball. Therefore, it will bounce higher with the same amount of force. Here are some more examples of such kind of potential energy, that is elastic potential energy. For example, a coiled spring possesses the elastic potential energy. An archer's bow with the string pulled back, it is an example of elastic potential energy. A stretched rubber band, saucer balls before players kick them, a diving board just before someone dives it. They all are the example of elastic potential energy. Chemical potential energy. Chemical energy occurs when energy is released during a chemical reaction. Potential chemical energy is the energy stored in the bonds of these chemicals which are ready to react with another chemical. Some examples include a charged battery. It is an example of chemical potential energy. Some chemical reactions are ready to take place, and during these chemical reactions, an amount of energy is released. Explosives. Green leaves before the sun shines on them. Then gasoline before it is ignited. Fireworks before they are launched. Wood in a fireplace before it burns. Iron before it gets wet and rusty. Fruit juice before it ferments. The wick in a candle. They all are the examples of chemical potential energy. Electric potential energy. When we see a light switch that is off, you cannot see the charge that is waiting to flow through the wires, but actually a charge is waiting to flow after switch is closed. This is an example of electric potential energy. That potential is actually blocked by an off switch. The other examples are an incandescent light bulb that is turned off, car's headlight before they are turned on, a radio tower that is not working, a cell phone that is turned off, solar cells at night, a black light which is turned off, a television before it is turned on. They all are the example of electric potential energy. Nuclear potential energy. Nuclear potential energy is stored in the particles of an atom. When the atom is split, for example, in nuclear fission, or atoms are combined, which takes place during nuclear fusion, then energy released actually becomes the kinetic energy. Magnetic potential energy. Like gravitational potential energy, magnetic potential energy affects how items work based upon their position. Items with high magnetic potential energy, such as a metal spoon or ball bearings, they respond strongly to a magnetic force. Objects with lower magnetic potential energy, such as a plastic spoon or a rubber ball, are not as affected by magnetic pull as these get affected. So they possesses the items made up of iron possesses higher magnetic potential energy. The items which are non-magnetic in nature actually possesses very little magnetic potential energy or no magnetic potential energy. So, we talked about the forms of energy, we talked about the states of energy, we discussed about the states of energy. Now, let us see what are the various uses of energy in our daily lives, right? Starting with the residential uses of energy. When we talk about residential uses of energy, these are the most basic uses of energy. They actually include watching television, washing clothes, even using the heating and lighting at home, taking a shower, working from home on your laptop or your computer like this, running appliances and cooking. The residential uses of energy account for almost 40% of total energy. 40% of total energy use in this category of use is also the highest globally. This can be attributed to the lack of education offered to the public on how to conserve the energy they use daily, or to the lack of energy conservation products which are available in the market. Commercial use of energy. Commercial use of energy is what energy is used for in the commercial sector. This includes heating, cooling, lighting, air conditioning of commercial buildings and spaces, the power used by companies and business throughout our cities for computers, for fax machines, for workstations, for copiers, just to name a few. There are a number of applications in the commercial category too. The uses of energy in commercial space is more or less similar to the use in the industrial space. Energy saving here, though, is targeted at the corporate world rather than at individuals. The players in the sector of energy conservation should introduce energy saving campaigns in order to curb the culture of waste present at our places of the work. Transportation. The transportation is 100% dependent upon the energy. Our 70% of petroleum used actually goes into the transport sector. The transport sector includes all vehicles from our personal cars to trucks to buses to motorcycles, etc. It also includes the aircrafts, the trains, ships, pipelines, etc. The transportation sector can be very vital in the overall quest for energy conservation. Innovations such as the introduction of more fuel-efficient vehicles and development of alternative sources of energy for our transport system can greatly help in the saving of the energy. Industry. Industrial energy use is predominantly used for production as well as for lighting and other business uses in the manufacturing industries. Industrial production makes up just over half of all global energy use and is expected to grow by a similar 1.5% globally each year through 2035. So this was about the various uses of energy in daily lives, residential, commercial, industrial, transportation. Now let us talk about conversion of energy among various forms, right? Let us also talk about the conservation of energy, about the law of conservation of energy, and let us also talk about the physics of power plants. So I have covered in this video, I have covered the various energy conversions taking place in thermal power plant, in hydroelectric power plant, in nuclear power plant. So let us talk about conversion of energy. We know that energy can and often does change from one form into another. For instance, a car battery, which is a form of the chemical energy, but produces the electrical energy which is needed to run the headlights of the car. Likewise, a diesel locomotive burns diesel fuel to produce the electrical energy which is needed to drive the engine's wheel. Such as complex processes such as the process of producing electrical energy through the combustion or burning of fossil fuels typically require several energy transformations or conversions. The conversion of energy is actually based upon the law of conservation of energy, which is the first law of thermodynamics. It states that these transformation, that actually this describes the transformations. It states energy can neither be created nor be destroyed, it can only change in form. So energy can neither be created nor it can be destroyed, it can only change the form of itself. By any time an energy conversion occurs, some energy is actually lost, and typically this loss of energy is in the form of heat. So for example, for every unit of fuel that is burned, only about 1/3 comes out as electric power, which would seem to violate the first law of thermodynamics. But actually, it is not the violation of the law, but the energy that is lost during the conversions. So we can see how much amount of energy gets wasted as gets lost as heat while converting the electricity, while generating the electricity by burning the fossil fuel. Let us talk about the physics of power plants. It is actually about the conversion of various forms of energy. Let us talk about the physics in context with the thermal power plant. In a simple thermal power plant, for example, some fuel such as coal or natural gas is burned. This causes conversion of chemical energy. It is basically the conversion of chemical potential energy contained in the fuel into the heat energy. The heat energy so produced is used to heat water in the boiler, and hence the steam production takes place. The steam then turns or rotates the steam turbine, which actually produces the mechanical energy. This mechanical energy is given as input to an alternator or electrical generator, which produces the electrical output. The basic schematic representation of a thermal power plant is here. This is the boiler in which fuel is burnt, and the heat so produced is used to convert water into steam. That steam is injected to the turbine, which is responsible to rotate the blades of the turbine. To the shaft of the turbine, electrical generator is coupled. So, it rotates the generator, which in turn produces the electricity. To complete the process, the steam coming out of the turbine is actually condensed in a condenser. It is converted back to water, and again with the help of the feed water pump, it is sent to the boiler for its conversion into steam again. Let us see the physics of hydroelectric power plant, the basic working of hydroelectric power plant. We know that it develops hydroelectricity to utilize the potential energy of the water. In hydroelectric power plant, water is stored in a dam, which is said to be the hydroelectric dam, which is located at upper level from the ground, especially any hilly areas. Waterhead is created by construction of the dam across any river or lake. This type of waterhead store huge amount of potential energy. The larger the height of the dam, higher is the amount of potential energy contained in the water of that which is stored in that dam. The water fall into water turbine through certain arrangement definitely. The water fall into water turbine and the potential energy of water is converted into kinetic energy. This kinetic energy is converted into mechanical energy at the turbine shaft. A hydroelectric generator or alternator is coupled with the turbine shaft to convert this mechanical energy into electrical energy. This is the representation of hydroelectric power plant dam. This is the reservoir behind the dam. This is the penstock through which water is brought to the turbine. This is the power station containing turbine and the generator. Physics of nuclear power plant. Physics of energy conversion in nuclear power plant. In a nuclear power plant, heat energy is generated by a nuclear reaction which is called the nuclear fission. Controllable fission is possible. That's why we are able to harness the nuclear energy in the form of by the nuclear fission reaction. Heavy elements such as uranium U-235 or thorium U-232 are subjected to nuclear fission reaction in a nuclear reactor. A large amount of heat energy is produced as a result of the fission reaction. This heat is transferred to the reactor coolant. The reactor coolant may be water, gas or some liquid metal. The reactor coolant is actually responsible to transfer the heat which is generated inside the reactor as a result of fission process to some other circuit where water gets converted into steam by absorbing this heat. The heated coolant is made to flow through a heat exchanger where water is converted into high temperature steam. The generated steam is then allowed to drive a steam turbine. The steam, after doing its work, is converted back into the water in the condenser and resent to the exchanger again. The steam turbine is coupled to an alternator which generates electricity. So, what are the various conversions of energy? The nuclear potential energy gets converted to heat or thermal energy. That thermal energy actually raises temperature of water and converts it into steam. That energy contained in the steam is converted into the mechanical energy with the help of the turbine, and the mechanical energy output of turbine is given as input to the generator to convert this mechanical energy into electrical energy. The basic schematic representation of a nuclear power plant is here. This is the nuclear reactor, this is the heat exchanger. Through a piping circuit, the coolant flows in the heat exchanger. Heat exchanger contains water. that water gets converted to steam, which is sent to the turbine, which is coupled to the generator. The generator provides electrical output, which is sent to the grid or the power system. The steam coming out of the turbine is condensed, converted back to the water and sent to the heat exchanger again for the conversion of water into steam, and in this manner the cycle is complete. So that's all about this lecture. Thank you.